Hello, everybody, and welcome to the 40th episode of the Hyperthesis podcast. I'm Liam.
I'm Feely.
And I'm Patrick.
So, before we talk about anything, I think we should talk about how this is going to be the last episode of our third season. Is it? Yes, the last episode of our third season. 40 episodes. Holy smokes! We're 10 away from 50, so we should do something special for 50 maybe. Now that I've said it, I have to hold myself accountable for it. Yeah, so we're gonna take like a 2 to 4 week break, and we're gonna do some things, and then we'll come back with more science to talk about. But until then, today we're gonna be talking about black holes and different types of black holes that exist in our universe. But before then, does anybody have an intro topic they'd like to discuss?
Yeah, well, this intro topic just came to my mind literally a few minutes ago because I was busy working on something else. But since we are talking about black holes, I think my intro topic could be all like ideal units of measurement. So, what do I mean by that? Scientists, we're so used to using the metric system. I mean, well, maybe not for some Americans, but the metric system is the go-to for the standard international unit, basically. But Americans are more used to the imperial system, where feet, yard, or whatnot. But there are also other units of measurement that's been used over the course of human history, and a lot of them are based on body measurement. For example, the foot, right? Like that's pretty long, 12 inches for a foot. I mean, is a little bit weird. But for example, in my country, the equivalent to foot that people use is we call saw, which means elbow, like one elbow. So basically from like your wrist to your elbow, that's like a foot. It's like, well, that's kind of reasonable. And like for an inch, like what is an inch? So we also have like our different unit of measurement that's actually based on how the body proportion work. So I wonder, we have defined meters and seconds and things almost arbitrarily. Somebody just picked that thing. That's why I think as physicists, sometimes we love, especially theorists, to use natural units, and because things are ratios. So I wonder, what do you think are ideal units of measurement when we talk about things in terms of, well, first theoretically, second is practically, right? Should you use yard? Is it more make sense to use mile or nautical miles? Like, what would be your ideal stuff?
Yeah, I think metric system, right? I think the whole point of that is that it's easy to convert between things because you just slap a bunch of powers of 10 or 1 over 10 on things. And I think that's kind of the power of the metric system. But yeah, I think I don't want to say natural units because when physicists say natural units, they mean something that's a bit dangerous that you got to be careful about. You're setting your units equal to 1. But I say like for example, what you said, measuring height in feet. In Canada, we use the metric system, but we also kind of jump between imperial and metric. So when people ask me my height, I say I'm 6'3", 6 foot tall plus 3 inches. Right? I'm a tall guy. Because it's more natural. At least it feels more natural to say I'm this many feet because everyone knows like roughly how big a foot is. It feels more natural to give your height in that than instead of saying like I'm something point something meters tall, or at least to me because I
That
grew up with it, right? And so when you measure distances in astronomy, you say, oh, the universe is so large. I'm not gonna say from this planet to this or this galaxy to this galaxy is like some enormous amount of meters. You're gonna say it's in light years because that's how long it takes light to travel. So that's some unit of measurement that you use that's a bit more natural in a certain situation, I think.
well, you say you know roughly where 6 feet is, right? But I grew up with the metric system. So I know roughly where 150 centimeters is, and you know
Yeah.
exactly where each 1 centimeter, roughly 1 centimeter is. And when you start knowing, oh, this is 160s, feels like this is like what's around 160, this is around 170,
Hmm.
and I thought before that 12 inches or 1 foot is around 30 centimeters, right? That's what the rule is, but it's not exact because I was approximated wrong for a very long time because I would use 2.5 centimeters for inch instead of 2.54, but 0.04 adds up. So when you calculate height, it's like, well, no, it's 6 foot is not 180 centimeters. It's more because there's these decimals that I wasn't considering.
It's interesting though. Looking at it from different perspectives because I've talked to American people who are like, oh yeah, Fahrenheit seems more natural because a change in a degree Fahrenheit is, I guess, not so noticeable, but it kind of goes within the limits of the body. So if it's 0 degrees Fahrenheit, it's very cold. If it's 100 degrees Fahrenheit, it's very hot. Whereas with Celsius, if it's 0 degrees and it's based on water, water freezes and it's kind of cold, depending on where you're from. Whereas if it's 100 degrees outside, you're dead. Um, but it's also interesting to see the history of where these came from. Like what was mentioned, where the length between your elbow and your hand is the length of a foot. But slightly, I guess, more scientific, but still kind of arbitrary is the meter, which is 1/10,000th the distance, or it might be it's 1/10 millionth, or yeah, 1/10 millionth of the distance between the North Pole and the equator as running through Paris. So it's based on just an arbitrary measurement of the Earth.
In a way, it has also, at least for me growing up learning about meters, it also have a like practical body proportion too. So in the army, we teach us to like put ourselves into an array or I don't know formation and stuff. There's like a certain length between person, right? And we use meters, but like, oh, you want to be 2 meters apart? What is a meter, right? So the way we do it is you put your arm out and you go from your tip of your finger to around like in the middle between one of your breast. So let's say if I put my right arm out from the tip to like the middle of my right breast, for example, that's like roughly a meter, and you kind of measure that between two persons, so you connect them, and it's roughly around 2 meters. So there's like these kind of things that I kind of want to take note of all the time, like I try to measure, for example, like your knuckle, right? You see your finger on your hand has three partitions, right? It would be nice to know how long one partition is, so you can measure things in life by comparing to your digits, right? I think that would be really useful, and I think some of these unit of measurement probably come from that, like your hand, for example. If you know exactly, you measure how big your hand is, and you can just like, oh, I want to know how long this thing, and you just compare your hand, right?
Far as I'm concerned, yeah, it doesn't really matter what units you use, but it's nice. Metric is nice because it's like one unit that everyone around the world can do science with, and you don't have to read a publication and be like, all right, I got to convert all these units everywhere. And it's just like one agreed upon thing. And now we're defining physical constants in terms of metric units and stuff through experiments. And but at the same time, I don't think I don't think there's anything wrong with using like other unit systems. It's just if you're going to, you have to be prepared to convert to metric, I think.
One, I guess, measure that I really personally don't like, but it would be impossible to change, is the second. The second is so arbitrary. It doesn't really make much sense, but we're stuck with it. But it'd be nice if like we could have some sort of metric version of the second. So instead of going in spaces of 12 or yeah, I guess kind of base 12, it's just base 10 instead.
I feel like the second is kind of natural though, because like kind of your resting heart rate, right? Like your heart beats roughly every second or so, or I don't know. That's the way I think about it, at least. It feels like one, two, 3. It's like kind of this natural, like, but again, I guess I grew up with seconds, right? So I don't know.
I think you have to look back at how time is divided in the ancient too. I think it seems like Mesopotamian time, like Babylonian. I'm not sure. I think that's where they start like having like the word minute, for example. Why 60, right? But why 24 hours in a day? So I think that there's like pretty good reason for like things are divided by 60. I think also the symmetry of the circles, why 360 degrees. There are auto system actually for like radians, for example, we use. They're not degrees, right?
I think the base 12 though comes from a different way of counting on your hand, from what I understand, because I think how it went was if you take your fingers, each one has 3 kind of divisions, and in total there are 12 divisions on your finger. I think that's how that was a way of counting that was very common in ancient times, and that's why so many things that have stuck around since then are base 12, and so it's 60 seconds, which is just 12 times 5 or 24 hours.
Hmm. And going back to the imperial and metric too, like, a lot of imperial stuff is not decimal based. For example, like, I can add pretty easily, centimeters, but foot and inch, I have to do it twice because I add foot and add inch and have to put inch into foot if it's over 12. It's more involved process for me. And it's like, well, there's probably a good way to do it or convert things to all inches. Like, why don't you say, oh, you're 112 inches tall, right? Like, or something like that. So, and it's kind of strange. To me, it reminds me of Roman numerals. They don't have zero, right? Like, they just imagine try to do all your math with no Roman numerals.
Yeah, that'd be brutal. But I think that's what I was saying at the beginning, right? Is that like the power of the metric system is the prefixes. It's that you measure things in meters or centimeters, which, there's 100 in a meter, or, like kilometers or nanometers or whatever. They're all just these, you multiply numbers by 10 to the whatever, like 10 or 100 or 1,000, or divide them by 100 or 1,000. So when you convert from meters to centimeters, that's super easy. But yeah, in imperial, it's like, all right, I have yards and feet and inches, and like then you have, yeah, it's weird.
And also a question of language too, right? Like, these are, in a way, language to talk about math. You could say the same thing about language to talk about anything else. For example, why is English and German or like Latin based language quite good at science? For example, is the way the tenses work, the way adjective work. Like, my language, for example, is when I read it in science, it's kind of difficult compared to reading it in English because we don't have that many space bars. For example, we just everything's just one blob, and people are like, well, how do you read this? Like, when you read like Japanese or Chinese or Thai, like, even though they're quite different, but you can see very few spaces between words, and you have to take it upon yourself to figure out what's doing what. But it became pretty intuitive. But in a sense, when you try to write something logically to form certain things, it's easier to write it in English sometimes. Or even, I don't know German, but I think the way German handle adjectives is better because it's much more clear, because I think they combine adjective and noun to get into one word. And it's like, oh, so you don't have to worry about like, well, which one is it's going to emphasize or talking about,
Yeah, I think you're right. I think German was actually going to be the language of physics before World War II happened, and then English took over. So unfortunate for the Germans, but here we are. For the sake of time, I think we should move on to the main topic, which I will be, I guess, I don't want to say presenting, but I'll be leading it today. So today's main topic is about black holes. Different types of black holes. So, I mean, we've talked about black holes probably almost every episode they come up somehow.
Yeah, I think I want to, before you get into all these type of black holes, I want to comment on, I think we discussed briefly or maybe extensively a couple days ago, maybe yesterday. I'm losing track of time this week. But
Yes.
you mentioned that black holes are not true singularities. I mean, real black holes, are not true singularities. I feel like most people, including me, for the longest time, thought black hole was defined such that this collapse in space time that it's go just to infinity. But practically, infinity doesn't manifest in the physical world, right? Like there's still mass, but the black holes are confined, so it's not a true infinity divergence point at the black hole, or is it?
Yeah, well, we most physicists would tell you it isn't a singularity because a singularity is in general relativity. That's where you're basically like somehow space time breaks down at the middle of a black hole at the singularity, which tells you that your theory doesn't work there. Um, I mean, we don't have a complete theory of gravity, so maybe there is a singularity, but I think most people who study black holes will tell you there really can't be. Um, if you just go by like kind of physical intuition and observations of the real world and stuff like that. Um, so somehow space-time isn't a complete description of the universe. I think that's like the gist of it. And then we're trying to discover and learn about quantum gravity, which will probably improve upon that and then maybe resolve this singularity, which we people think it should resolve the singularity. But again, we don't really know at the moment.
Yeah, and black holes to me, the word kind of a little bit misleading. At first, it was correctly leading, but the more you learn about black holes, the more you learn about physics. You're like, yeah, it's not exactly, well, we call it black, but like if Liam is gonna talk about an analog black holes or maybe acoustic black holes and stuff. Those could maybe they're not black. They just it's a type of behavior, but this doesn't necessarily has to be black.
Yeah, I'm not gonna talk about my acoustic black holes today, I don't think. Um,
Not holes even. They don't have to
yeah.
be holes either.
So black holes, they were first predicted by, general relativity, and they're these according to general relativity, they're kind of these eternal objects. Things get sucked into them. Not even light can escape once it goes past this edge of them called an event horizon. So they kind of just eat things and just exist essentially. And since light can't escape, they're black by definition. They can't reflect light. Like when you look at a car driving down the street, a red car, you're seeing it's absorbing all these colors of light and it's reflecting predominantly red light into your eyes. So you see a red car. Well, black hole, if nothing can escape from it, then you can't see it. There's no light coming out of it to hit your eyes. But then, Stephen Hawking came along and said, okay, black holes aren't perfectly black actually. You take into account quantum effects near their event horizons and they can actually radiate. So they're not quite black holes, but the ones in our current universe aren't really radiating, so they're pretty much black. Um, but because black holes can radiate at some point in the universe's timeline, they essentially will glow like a black body at some point and eventually evaporate away.
So there was this thought that came to mind that when I look at analog black hole, for example, the acoustic black holes where it traps, this event horizon for sounds, the sounds can't go through, but light doesn't care. They just go through that so-called quote unquote black holes easily. So I wonder if there's some kind of things, analogous things in gravitational black holes that we deem to be all absorbing, or nothing can pass, something like maybe the proposed dark energy or dark matter that just ignore space-time. I'm not sure. So maybe there's something like that.
Yeah, I know this is a very interesting topic in dark matter and dark energy research, just because, one, we don't really know what they are yet, but we do know that dark matter is attracted gravitationally to objects in space. And so in galaxies, we find this, I guess, clump of dark matter around the central black holes. But for dark energy, it's theorized that that might be like anti-gravity energy kind of thing. Again, no clue what dark energy is. We have some guesses, but it would be very interesting to see like if something like dark energy could escape a black hole, because it's repelled by mass instead of attracted to it.
I want to believe dark energy is anti-gravity because every other fundamental force has positive and minuses, like, electromagnetism has plus and minus charge and stuff like that. And then gravity's kind of the only one where it's only positive. There's no like negative mass. You don't push on an object and it goes towards you kind of thing.
Well, that's why I think quantum gravity is trying to kind of resolve that a bit too with the graviton. If graviton exists, anti-graviton must exist then.
Well, you got to be careful because an antiphoton is just a photon. So an antiphoton is the same thing as a photon. So there technically, I guess, is no antiphoton.
Well,
Which
but the
is
fields can also,
electromagnetism.
but the field can cancel itself out. But for gravity, you can't, right? Like if you add more mass, for example, or you curve it more, it's gonna curve more. You can't uncurve it.
Yeah, that's a good point, but
The anti-graviton, instead of curving in the let's say in the one direction, is curving in the opposite direction.
Yeah.
Because the anti-photon is basically the same photon with the opposite field.
I think an antiphoton is just the same thing as a regular photon.
Yeah, it's a regular photon with the opposite. If you think as wave, this opposite direction, opposite amplitude direction.
Does it have opposite direction? I don't know.
Well,
I mean, for an antiphoton and a photon, they are the same thing. So it's possible that a graviton could be its own antiparticle and behave similarly to a photon. It just depends on how the fields interact.
Yeah, exactly. Instead of like electric field E, it's gonna be minus E, right? Like that's why they kind of cancel out.
Anyway, we should black holes, back to them. Yeah, I'm not sure. Acoustic black holes are a bit different because, I mean, they're not real black holes. They behave like black holes for sound waves, but obviously things can move faster than sound waves, like light. Whereas in our current understanding of the universe, not much can move faster than. I mean, there's theorized things that can move faster than light, but they cause their own problems. So that's a hot debate at the moment.
One thing I just want to, I guess, clarify for those not as familiar with black holes, and something that was discussed, is that we have this idea that they're like these vacuum cleaners of space where they'll just suck up anything nearby. But the movies like Interstellar get it right, where things can actually orbit stably around a black hole. So we have like black hole star binary systems where they're stable and there's not too much going on. It's only when you get close enough to the black hole that tidal forces really come into play. And of course, if you are stationary around a black hole, then you're definitely going to fall into it like any other massive object. But they don't suck everything in that goes by them. It's only if it's close enough and not in a stable orbit.
Yeah, and so I'll come to that soon about those binary systems a little bit, actually, and also accretion disks, because like you can't really see black holes per se, but you can indirectly see them through different methods, and one of them is that turns out that black holes have a lot of stuff orbiting them sometimes, and you can see that. So yeah, black holes. I don't even need to give an intro on what a black hole is now because we just talked about it for so long. And my what I wanted to talk about is how astronomers and cosmologists generally kind of classify black holes, and they divide them into, there's more than 4 categories, but there's 4 kind of big categories, and those are based on the mass of the black holes. So these different mass ranges which define these classes of black holes, they kind of change sometimes. So like how, astronomers decided Pluto wasn't technically a planet and it should be a dwarf planet. Sometimes they change their mind on what one type of black hole might be classified as. So we're still working on it. We still don't perfectly understand black holes, as you might realize by now. So the first class are called stellar mass black holes. So when a star with roughly more than 8 times our sun's mass, which we call a solar mass, when one of these stars depletes its fuel supply, which is where the fuel is hydrogen, its core collapses, it rebounds, and then it explodes as a supernova. And there's different outcomes of a supernova. You can get different types of stars produced. However, if the star had around 20 times the sun's mass, excuse me. So if the star went supernova with around 20 times the sun's mass or more, the core will collapse into a stellar mass black hole, which themselves can have, well, their masses are on the stellar range, hence their name. So they can have masses ranging from about 3 times our sun's mass, um, which is around the smallest one we've ever seen. I think it's like 3.5 solar masses, and it could go up to about 100 times our sun's mass. So that's pretty heavy, but compared to some of the other ones, they're quite small. I mean, you think of the Earth is massive, and you think of the sun's even more massive, and then you get these things that are 100 times our sun's mass, and they're still considered like on the smaller end of the black hole spectrum. So it's kind of wild to think about. So black holes, like we said, they can eat things. They can continue to gain mass through collisions with stars or gas or even other black holes. If two black holes bump into each other, they just kind of merge into a bigger black hole, which is kind of cool. And although stellar mass black holes are many times our sun's mass, they're quite small. So black holes, they're very dense, which means they have a very large mass to volume ratio. So their volume ends up being a lot smaller, and they have a lot higher mass. So they have very high densities. So these stellar mass black holes, they can be anywhere from 20 kilometers to 300-ish kilometers in diameter. And for scale, the diameter of the Earth is about 13,000 kilometers. So that's pretty. They're pretty small, realistically. But they have extreme gravitational pull. And how do we see these stellar mass black holes? Because they're pretty small. If you look out into the universe, one of the primary ways we see things is optically. So we see stars in distant galaxies emitting, or we see stars in our galaxy emitting light. And we see galaxies that are really far away emitting light. So a lot of these stellar mass black holes get kind of detected through what's it called again? What you were saying earlier, Patrick. These systems consisting of two stars called binary stars. What ends up happening is that one of the bigger stars and these two stars orbiting each other, there'll be a bigger one, and it'll eventually at some point in time turn into a black hole. And as this black hole orbits the other star, it'll kind of strip off gas from that star, and because of that, it ends up kind of creating a lot of X-rays that fire off into the universe. I don't know the exact mechanism of that. I don't know if anyone here does, but essentially, yeah, they produce a lot of X-rays, and we can detect them through that. So that's one way that's one of the primary ways we see them optically. And I think so far we've only seen about 50 suspected or confirmed stellar mass black holes. However, in the Milky Way, but it's theorized there's hundreds of millions of them in our galaxy alone. So they're quite common, but they're hard to spot on their own. You need something happening nearby them to see them. Another recent development that we can detect these stellar mass black holes is gravitational wave detectors like LIGO. So in 2015, that's how they actually detected two stellar mass black holes orbiting each other and then merging into a single black hole. So we have this kind of new way to see stellar mass black holes. The problem is they need to kind of be doing something similar to these binary systems. If you just have like kind of a stationary black hole in space on its own, you're gonna have a hard time seeing it. It needs to be doing something.
It sounds like the classification of gravitational black hole just depends on the mass or the size, basically, right? There's not much to it, right? It's not like a Power Ranger or something. Oh, this is the red black holes because it has special characteristics on it. It's just like it's the same thing, buddy, but it's just like tiny, a little bit bigger, a little bit smaller. It may come from different stars, but it's essentially the same thing, right?
Yeah, and that's it. All these different types I'm going to talk about today, all four of them, I guess, they're all kind of they may have formed differently, and they may be very different sizes and masses, but they're effectively kind of the same. And there's another episode that I'm going to give in the future where I talk about the different theoretical models we have to describe black holes. So the very popular one's a short shield black hole. That's like a stationary black hole with no charge or spin. But what happens if you put spin on it, or what happens if it has a charge? And I'm not going to talk about that today, but in a future episode I will. But today I'm just talking about basically different mass black holes.
It's just at that point, it's important to mention the no hair theorem, where essentially black holes don't really have any defining features physically aside from their mass, their electric charge, and their angular momentum. So essentially, if it's spinning, how large it is, and if it's charged or not defines a black hole, but there's nothing special about each individual black hole. Like if you had two black holes with the same mass, electric charge, and angular momentum, then there's no way to actually differentiate them.
Yeah, in again, next season, we should have like, you know how Discovery Channel has a Shark Week? We should have like a black hole month, because this no hair theorem also involves this thing called the information loss paradox, which maybe we've mentioned before, but I wanted to do a whole episode on it and different potential resolutions to it. So maybe I can do this episode about different models we have for black holes and then information loss paradox and blah, blah, blah. Because that's all interesting stuff. So yeah, stellar mass black holes, they're on masses of the order of our sun, to 3 to 100 masses or so. Smallest we've seen is 3.5 ish. So the next one is these are kind of my favorite. The next class are the supermassive black holes. These are the big boys, the ones you see in movies like Interstellar. They're the ones that are they're very hard to comprehend. Almost every large galaxy, including the Milky Way we live in, has this supermassive black hole at its center. It's like the nucleus. It's the thing holding the whole galaxy together. Well, not completely, because there's dark matter and stuff like that going on, but it's kind of it's like an atom, right? You have its nucleus holding things together. It's like the nucleus of like most galaxies. And these things are big. They can be anywhere from 100,000 times the mass of our sun to billions times the mass of the sun. So they're a lot bigger than these stellar mass black holes I talk about. And observations of galaxies tell us that supermassive black holes, they may have formed, we don't fully understand how they formed, but one of the theories is that they may have formed in the first 1 billion years or so after the birth of our universe, so after the Big Bang. And these black holes may have formed due to the collapse of supermassive stars, which had formed in the early universe. So they got kind of a head start on eating things, unlike the stellar mass black holes. So they were able to consume just galaxies worth of material over time, and that's why they got so large. Supermassive black holes are a lot easier to see than the stellar mass black holes because they're so big, and they often are surrounded by this large accretion disk of gas that rotates around them. So they kind of feed on this gas, and because their gravitational forces are so strong, these gas molecules and particles, they'll orbit this black hole extremely fast, and they emit radiation as they do that. So these supermassive black holes can shoot these jets of radiation, or they have these big disks around them. So if you've ever watched Interstellar, the black hole that they have in that movie is actually a real physics simulation of a black hole, and has this big orange kind of looking, big whitish orangish. I think it's orangish. Maybe it's just whitish, but it has this giant disk around it. And you would actually see that. That would be the radiation emitting light as it orbits the black hole. And recently, we actually were able to take an actual image of a black hole, which is that orange kind of blob that we've talked about before, through the Event Horizon collaboration. It was a supermassive black hole called, is it Messier or Messier? I think it's Messier 87. So it's that kind of orange blob image that they were able to take with a radio telescope. And that wasn't the black hole itself, because again, you can't per se see a black hole, but that was the radiation orbiting the black hole emitting light. So we detected the light all the way here on Earth. So pretty cool stuff. The largest supermassive black hole that we know of is called Ton 618. I don't know why it's called that. Maybe because it weighs a ton. But probably not. It probably has some actual acronym. But this black hole is the king of kings. It is the biggest of boys. It's visible approximately 18.2 billion light years from Earth, shining with the brightness of 100 trillion suns. and it's a whopping 66 billion times the mass of our sun. And this is black holes. They're a lot heavier. They have a lot more mass than they have volume typically. But this one's so large that you can fit 11 of our solar systems across its diameter, and that doesn't even include the giant gas clouds around it. This thing, it's inhaling galaxies. It's inhaling just tons of matter all the time, and it's super hard to comprehend these things. They're pretty wild.
Yeah, that is certainly insane to think about, just the size of these supermassive black holes, especially the fact that we have Sagittarius A star at the center of our galaxy, and it's small compared to this one at only, was it like 100 million times the mass of our sun, or somewhere along those lines, and to think that there's this massive quasar, which I believe they're called when they're shining quite brightly.
Mm-hmm. Those are the big jets shooting out of them,
yeah.
I think.
Yeah, the fact that there's something this bright and this big in the universe is kind of terrifying.
Yeah, it's hard to imagine. Like, you think of how big the Earth is, and it's just massive. But then you think about, like, the sun's even just so much bigger than that. But then you think this thing's 11 solar systems in diameter, and it's just a single black hole. It's like, that's massive, man. But that brings us to the third class of black holes. So we've talked about stellar mass ones, supermassive ones, but what's happening in between? Where are the medium-sized black holes? These so-called intermediate black holes. Mass is too big to be stellar mass and or supermassive, and mass is too small. Oh, sorry. Mass is too small to be supermassive and too big to be stellar black holes. So these middle ground black holes are actually a bit more mysterious than the previous two we talked about, and we don't fully understand them. Turns out there's not a lot of them. We haven't been able to very well detect them compared to the other black holes. There's other black holes you can see with gravitational lensing and gravitational wave detectors and these X-ray binary systems, but these middle ground ones, we seem to not be able to find them very often. So according to our current theory, there should be a continuum of black hole sizes because over time, collisions between stars and other black holes, you'd expect some of them to be in between the smaller and bigger sized ranges. But we can't find them essentially. And we have some potential candidates, but they're so far away that we can't really tell with good certainty. We can't say for certain that they're these intermediate black holes. We could be missing something. But a very cool thing is that pretty recently actually, in 2019, we actually used these new gravitational wave detectors to directly detect the existence of an intermediate black hole. So there was two stellar mass black holes, each weighing 85 and 65 solar masses orbiting each other. And when they merged, they created a 142 solar mass black hole. So that's just above the range of a stellar mass black hole, and it fits in the intermediate range. So I don't know. Maybe it's because maybe we're at some kind of stage in the universe where we haven't existed in the universe hasn't been around long enough for many intermediate black holes to form, and we're just kind of at the beginning of that stage because we witnessed one being born, and it's still a pretty small intermediate black hole, but it's something at least. So there's a lot more work to do in that direction and things to discover.
Also, if you are keeping count at home, the 85 and 65 solar masses combined does not equal 142 solar masses.
Very astute.
It should equal 150, but that energy was radiated away by gravitational waves, and some of which we detected. But that's really the only way that black holes can radiate energy, not from their accretion disk, is through gravitational waves. So they actually lost energy, in this case in the form of mass, by the production of gravitational waves, which we'll have to get into maybe in a different episode because gravitational waves are very, very cool.
Yeah, it's a huge leap forward in kind of astronomy because the only way we observe things in the universe the only things we used to was through light, right? You look up in the sky, and if there's something in between you and your source, or if it's not very bright, there's no chance you're going to see it. Now we can see things through gravity. So that's the more ways to do things, the merrier. And so those were the first three, and there's this fourth one which is more theoretical, but it kind of ties into dark matter a little bit, which is kind of cool. This fourth class of black hole, also very mysterious. They're called primordial black holes. And right now they're purely theoretical. But physicists theorize that these primordial black holes, they're black holes which formed during the first second or so of the birth of the universe. So very, very early in the universe, kind of like during the Big Bang. And in that moment, small regions of space-time could have had very, very large um, matter. They could have had very large densities of stuff, essentially, in these little pockets that formed as the universe was still expanding. And they'd be very, very small, kind of fluctuations in the density. So that you could have actually formed the little tiny black holes because of this, these so-called primordial black holes. And they didn't necessarily have to be extremely small, but they were small. They could anywhere from 10 to the minus 8 kilograms to a few thousand solar masses. So a few thousand solar masses is still fairly big. But you could get the really, really tiny ones, like 10 to the minus 8 kilograms, right? That's such a tiny amount. So these black holes would be kind of like the size of like nanometers or micrometers or stuff like that. So very tiny. So in theory, these primordial black holes, they wouldn't exist anymore because they would have actually been so small that they evaporated away due to Hawking radiation, which we also talked about. The smaller a black hole is, the higher its temperature is, and the higher its temperature is essentially the more likely it is to emit radiation and evaporate. So at least according to this theory, you wouldn't see really the smaller primordial black holes wouldn't exist anymore because they'd have radiated away by now. However, the more massive primordial black holes could actually still exist, and they're actually good candidates for being the seeds of supermassive black holes and even these intermediate mass black holes. And one of my favorite theories, I mean, I don't know how realistic it is, I've never done the math, but I think it's a really cool concept, is that these primordial black holes could actually describe dark matter. They've been getting a lot of increased attention in that regard.
Yeah, I mean, so this is, again, a hot debate in dark matter, but it's kind of gone by the wayside. Just in terms of all the dark matter, we can't really describe it with what are known as machos, or massive astrophysical compact halo objects, also known as primordial black holes. It could also be other objects like dark stars or very, very massive planets. But based on our observations, essentially, we know that all of dark matter is most likely not made up of these machos. So primordial black holes would be very cool, but they don't explain all of dark matter. Just wanted to throw that in there.
Okay. They're still working on it though. Yeah, like again, I don't know how realistic it is, and there's evidence for it and there's evidence against it. So it's a theory. We'll see how it holds the test of time. But so according to this theory, if conditions, so if you had certain primordial black holes formed during the formation of the universe with just the right amount of mass so that they could radiate down to a very small size, but they do it in such a way that they stop radiating as the universe cooled down, they become stable and they wouldn't evaporate completely. They could still exist in our modern universe. And they would exist as little tiny kind of micrometer sized black holes, which would be too small for us to ever detect using traditional kind of telescopes, or maybe even these gravitational wave detectors. So if they could kind of, essentially dark matter is this extra stuff in the universe that we can't see, but it has a gravitational effect. So I think if you look at like spiral galaxies, they're held together a certain way, but they're missing a ton of mass, and that's what we call dark matter. So maybe one of the theories is that these primordial black holes could exist out there and they could actually account for this mass. But again, there's some evidence for it, and some papers present really good evidence that really matches, and then some papers where you have people who don't like that theory, they have very good evidence against it. So it's someone's right, someone's wrong, or maybe they're both a little bit right and both a little bit wrong. But it's a bold claim saying that maybe these primordial black holes account for some of Earth's or some of the dark matter. And actually, in a recent publication, 2022, there was some primordial black holes were used to explain these for the James Webb Space Telescope, this new telescope that went out. You can see much further back into the history of the galaxy. they actually used the existence of primordial black holes to explain an unexpected, very large early redshift that they were seeing in the galaxies. Again, maybe they're missing something, maybe they're not. And in September 2019, which is even a bolder claim, there's a theory proposed that the possibility that a primordial black hole, which was about 5 to 15 Earth masses, and so that would be about 6.5 centimeters in diameter, could actually exist in near the Kuiper belt, because there's actually this kind of this theorized ninth planet that exists out there. We people have run some math, and they said according to gravity, we're missing a planet somewhere in our solar system. It should be there, but we can't see it. So some people predict that maybe this is a primordial black hole.
I remember reading this paper when it came out, and it's really funny because they actually have a picture of the size of the black hole. Since it's only 6.5 centimeters in diameter, they included an actual size on the in the paper, and it's just a giant black dot on the paper. But it was just really funny.
That is kind of funny, actually. It's just like, this is the black hole size. You could hold it.
Yeah.
Well, when I think about a lot of like primordial black holes and stuff, I'm like, why weren't in the early universe there were black holes everywhere? I mean, like things are closer, right? I mean, things weren't expanding as much. There must be a bunch of holes in the universe that exist for a long time. And Hawking radiation and stuff, but it takes too long for black holes to dissipate anyway. So they're probably still around, right? And my sci-fi kind of theory of hypothesis that the Big Bang is essentially like one massive black hole, but it gets to the point where it reached true singularity, like true infinity, and it's punctured to the dimension, and boom, black hole create another universe. Well, I'll just leave it there.
Yeah, there's some pretty wild. It's actually what, like, you say that and it sounds kind of like far out and kind of like, oh, that's a crackpot theory, but when you actually do like kind of the calculations and the math, it kind of looks like that. So that's where those theories even came from.
Right? Because well, Big Bang is essentially, to me, is like you do like time reverse theory. It's like, oh, is everything expanding? What if things just come to one point? Well, if what are things that come to one point? Well, that's like a black hole, but a very, very like infinitely deep black hole, right? Like, to me, there's not much of a crackpot. It's very, to me, it's very reasonable assumption that like eventually black holes would reach something, and perhaps that point of singularity, a true singularity, is when new universe gets created. But maybe the heat death of the universe, actually everything turns out combines to one massive black hole, everything, and then and just explode.
Yeah, there's a shocking amount of connections between black holes in the universe. Even like the fact that you have like a cosmic horizon on the edge of the universe and stuff like that. It's, again, this is all stuff that I don't know enough about to talk about, but I'm slowly learning about as I go through my studies. Yeah, so those are kind of the four main types of black holes, and you could argue that I guess there's three, and this fourth one is very theorized. Black holes. We'll talk about them more. But for now, Patrick.
Yes. So if you are interested in contacting us, whether you have questions about the black holes that we're talking about, or really anything, or if you're an expert in black holes and want to talk about them, we would love to have you on the show, and you can contact us through multiple different methods. The first being our Gmail account. So you can email hyperthesispodcast@gmail.com if you have any comments, queries, suggestions, or you want to be a guest on our show. We just had a giant run of guests, so we're more than happy to have more. So let us know. For social media, we are on Instagram @the Hyperthesis. You can follow us. You can like our photos. We'll let you know when there are new episodes being posted. And especially after our short break for the next about month, we will make sure that you are updated when we are getting things started again. If you would like to find us otherwise, we are on YouTube. We have begun re-uploading videos to YouTube, so you can watch a very cool graphic as you listen to the Hyperthesis, and you can listen to it wherever you go. If you have YouTube Premium, you can listen to it offline. If you want to listen to us not on YouTube, you can find us on Spotify, where we're based out of, as well as Apple Podcasts, Google Podcasts, Amazon Music, and wherever you get your podcast. So feel free to give us a rating, a like, a share, a subscribe, whatever you do with your podcasting service. And make sure to spread the word about our podcast. And again, if you would like to be a guest on our show, please send us a message through one of our many different methods.
Excellent. Thank you. Yes. Please tune in. If you have any comments, we want to hear them. Appreciate it. Yeah.
Absolutely.
All right. So back to you again, Patrick. You're going to be telling us a little story about the life of a star. So we talked about a little bit of that today, I think, and supernova and stuff like that, but we didn't get into it too much. So take it away.
Okay. Well, we did talk a lot about black holes today, but I want to delve more into, I guess, their parents, whether it's from these supermassive stars that may have existed in the early universe, or stars today that we are able to witness undergoing supernova and then could possibly form a black hole. So the life of a star is a very dramatic one for parts of it, but is for the most part quite stable. So before we get into the formation of black holes and other things, we want to look at the birth of stars. Now, in order to see this birth, we have to travel to a region of space that is filled with both gas and dust in this giant cloud called a nebula. And these nebula, or nebulae, if you're talking plural, are the breeding grounds of stars. I would highly recommend looking up images of them, as they can be quite stunning and beautiful, especially from Hubble and also newly from the James Webb Space Telescope. But they're these truly massive bodies that can cover light years of space, and they're just giant clouds of dust and gas. And now these regions aren't really doing too much until something causes them to start moving. So, for example, the collapse of another star can trigger a shock wave that moves outwards through these giant clouds of dust and then triggers their clumping, because all of these particles are still affected by gravity. And once this triggering event happens, whether it's just some random collision, whether it's shock waves of some sort, will cause the gas and dust to start to collide with each other and start to stick with each other. And so over time, these clumps will begin to stick with each other, and there will essentially be a difference in density, and all of this gas and dust within a portion of the nebula, because many stars can be made from these nebulae, will start to clump together and get denser and denser as more and more gas and dust is collected in the center, and it clumps and then it collects more and more. And as it collides with each other and grows, it also gets hotter because there's a lot of collisions, there's a lot of friction, but there's also a lot of spinning going on. Typically, nebula will have some sort of angular momentum, which might not be apparent very, very far out since they're so spread out. But as you move closer and closer, and these giant masses start to compile, we start to see that they start to spin, and that causes things to heat up as well. So as it's spinning faster and these collisions are taking place, things are really heating up. And there's also an immense pressure forming at the center because of just the sheer amount of gas and dust that's built up. Now, at this point, it's reaching about 15 million degrees Celsius, so quite hot, and is known as a protostar. And once a critical point is hit in temperature and pressure, fusion of hydrogen begins in its core. And this is when the star actually turns on and produces energy and causes the star to become stable. So the energy released by the fusion of hydrogen in its center counteracts the force of gravity, so the star becomes stable and starts to burn, where the hydrogen is fusing and it's emitting a lot of light. And it's not just relying on the temperature from the collisions and the spinning. Now, this point of equilibrium happens with stars that are greater than a mass of about 0.08 times the mass of the Sun, or the weight of about 83 Jupiters. Now, for masses around that point and lower, these tend to just form what are known as brown dwarfs, and you might have a bit of fusion going on, especially with deuterium, which is easier to fuse than just pure single proton hydrogen, but they aren't really large enough to sustain the fusion. And so they don't stay hot for very long, and they become these brown dwarfs because they don't really emit light. Now, smaller collections of gas than about 83 Jupiters of weight can also form brown dwarfs, but they're orbiting a star, they might just be supermassive planets. However, for larger masses, because as we discussed, mass defines a lot in our universe, not just black holes, this is the beginning of a star's life, where it starts emitting light and energy, and it's very hot, and that's sustained for very long periods of time. Now, how long it lives for, or how long it's continuously fusing and emitting energy, depends on its mass. Higher mass stars will actually live for shorter periods of time because they're burning through a lot more of their hydrogen a lot more quickly. Whereas stars like our sun and smaller can go for billions of years. Our sun is predicted to have a lifespan of about 10 billion years to trillions of years even. Whereas these supermassive stars will only be around for about 10 million years. Now, we tend to measure the mass of these stars based on our sun's mass, as we discussed with black holes, and that our sun is one solar mass. So all these stars will fuse hydrogen at different rates, and their mass will also dictate how they end and where they go when all that hydrogen is fused. Now, starting with low mass stars, these are quite special because we haven't actually witnessed them dying. These stars are lower mass than our sun, so around 10% of the sun's mass, or 0.1 solar masses, are what define a red dwarf. And now red dwarfs are estimated to live between 6 and 12 trillion years. So given that our universe is only 13.8 billion years old, we still have quite a long way to go before we see these start to die out. However, unlike their more massive brethren, these low-mass stars are predicted to collapse slowly over billions of years instead of in one giant show of light and pressure and heat. And this transition will form white dwarfs. Now, these stars, since they're so small, they have a lot of convection even throughout their core. And so essentially what happens is that as the hydrogen is burned up, it stays in the core, but it's also convected out once it's converted to helium and new hydrogen replaces it. So essentially, these stars just become these giant helium stars, which form white dwarfs and slowly cool into brown dwarfs. Again, we haven't witnessed this yet. These are just theories. Now, slightly more massive stars, still under 60% of the sun's mass, may turn into red giants where they're expanding, but they never reach temperatures hot enough to fuse helium. And so their end stage is a white dwarf, then after trillions of years of cooling, a brown dwarf. Now moving to medium-sized stars, like our sun, and a little bit less massive and a little bit more massive on either side of that, so about between 0.6 solar masses and 10 solar masses, they will become red giants when their hydrogen core depletes. Now, there are many complicated processes that happen, but essentially helium can start fusing if there's enough pressure from the outside, or if in other words, if the star is massive enough. But helium fusion can happen with hydrogen fusion happening around it. So there's almost layers of helium and hydrogen fusion. And this can form a carbon core. Now, typically, these stars are not massive enough to fuse carbon, so they just kind of collapse in on themselves because there's no more energy pushing outwards. And this will create kind of a supernova, but essentially a white dwarf. And there are some very cool images from Hubble especially of these different solar nebula, which have been produced from a supernova of these medium-sized stars. And again, white dwarf will be the end result. So eventually our sun, once it explodes, it will become a white dwarf and then cool slowly. Of course, Earth will not be there anymore because it will expand into a red giant first, but it will be the end of the Earth. Now, for massive stars that are greater than 10 solar masses, this is where things get really cool and really interesting. There are many different ways that these stars can die, again, depending on the mass, but they typically end in a very dramatic supernova. So they're massive enough that once hydrogen has been fused fully in their core, it immediately starts fusing helium. Now, this helium is, again, fusing, and there might be hydrogen fusing around the helium core. And we can get subsequent layers of fusion as helium fuses, and then its resultant products also fuse. So carbon and nitrogen, oxygen, and all of those elements start to fuse. We get layers of different fusion. So there might be hydrogen, and then helium closer to the core, and then carbon, and then in the core we get even more fusion happening. For some stars, particularly between 8 and 12 solar masses, it will get to the point of neon fusing, or neon present in the core, and then through an electron capture process, this leads to neon burning, which sounds weird, but it does happen, and this creates a supernova, known as an electron capture supernova. We won't get into that, but for larger stars, they will continue fusing until an iron core is achieved. Now, iron is a very stable element. If it's kind of the stopping point for both fusion and fission to get more energy out of it. So iron, if you fuse it, you lose energy. If you try and split it, you lose energy. Because it takes more energy to do either of those to iron. So it's quite stable. Now, as the core becomes iron, you have these layers on top that are slowly fusing and adding to the core. And once the iron core has built up and grows to a mass that exceeds the Chandrasekhar mass,
It's
which is
Chandrasekhar mass. Yeah.
Yes. Yeah.
I know
sorry
this
if I
because
mispronounced that.
there's some he did something in some stuff I'm working on, so I have to say his name to people sometimes. I don't even think I'm saying it
Fantastic.
perfectly, but it's closer to that.
If you know how to pronounce it, please send us an email. But this Chandrasekhar mass, which is around 1.3 to 1.8 solar masses of the iron core, will essentially lead to electron capture of the iron, and no more fusion takes place, and the star will start to collapse, causing a supernova. Now, there are different types of supernova. There's type 1a, type 1b, type 1c, and type 2, which all do different things. Some involve binary stars. Others, for the most part, involve just solo stars. But we'll just talk about the solo stars now. And essentially, once fusion stops, there's no outward pressure. And depending on the mass of the star, it will all start to move inwards as the gravitational pull overcomes the now non-existent fusion outward force, and it collapses on the solid iron core. Now, there's an insane amount of pressure and heat going on here, but some of that matter will rebound off and create these stellar nebula, which is what we see, and there's also bright flashes of light. There's a lot of mass moving. But what can happen in the core is electron capture again, this time with the iron. And when you squeeze an electron and a proton together with enough energy, you form a neutron. And this is what leads to neutron stars, which are extremely, extremely dense objects where there is essentially no space between the neutrons. Whereas in an atom, there's a lot of empty space because you have the nucleus and then the electrons orbiting a relatively very far amount away. Whereas with neutrons, there's essentially no space between them. So it's a very dense but small object. So neutron stars tend to be on the order of 10 kilometers in diameter. Now, if the star is too massive and the core is too massive to even sustain a neutron star, and it's compressed underneath the Schwarzschild radius, then it will form a black hole, of which we've talked a lot about. And so this occurs when the remaining mass of the star is around 2 to 3 solar masses. So we have this extremely dense object just collapsing in on itself until it becomes a black hole. Now, there are many things we don't understand about star formation and death because we can't reproduce stars in a lab. But we have a lot of very powerful instruments, both in space, like the James Webb Space Telescope, and on Earth, like the Large Hadron Collider, where we're able to either observe or reproduce some of these conditions of star formation and star death. And who knows, maybe one day we'll be able to travel to a nebula or a dying star and witness these events firsthand.
Very nice. It's a good little summary episode of different types of stars and black holes, actually. I really like that. So thank you very much for that, Patrick. That was great. And thank you for joining us for the 40th episode of our podcast and the final episode